what, how, and most importantly, why. I don't think I have ever watched a short video that has left me asking more questions. And I can live with unanswered questions for about 5 seconds. So I got to digging, and soon I found out that this is one of the craziest inventions I have seen in a very long time. What you're looking at is called Rosmar H, and it is the brainchild of Romanian inventor Adrian Roșca. It has recently surfaced online, this prototype, where it got quite a bit of media attention, but Mr. Roșca has actually been working on this project for more than a decade. Unfortunately, Mr. Roșca suffers from a deadly combination of endless belief in his own invention and zero media savvy, which has led to him making some very bold claims. He also believes in his invention so much that he went to appear on TV investor and talent shows, where he presented his invention and made even crazier and bolder claims. He was also interrupted and promptly dismissed and never really given a chance to explain how his invention works. The recent media articles, they also just sort of prey upon these wild claims of Mr. Roșca, and they ridicule the invention rather than try to explain how it works. And the comments online, they pretty much do the same thing. And I kind of get it. To most people, this just looks unnecessarily complicated and the claims just look crazy. And so people think it's, vaporware or some crazy inventor or whatever, and they dismiss it. Well, today I'm going to play a combination of a Good Samaritan and the Devil's Advocate to fix all that. Because A, this makes a great thumbnail. B, I think that anybody who has spent decades of their own time and money and created something, they deserve to be heard. So I want to explain how this actually works. C, I think that the 0 to 100 kilometers per hour in 0.3 seconds, I'm confident it's actually possible with this invention. And D, this video gives me an excuse to make a working model of this car so that I can use it to explain how the actual car works. And here's the model. And the first thing I'm going to do with it is use it to hold your attention span hostage, because I want to talk about the why first, and then I'm going to explain the how. So why does the Rosmar car walk? Why doesn't it move like all the other cars out there? It doesn't, because according to Mr. Roșca, walking is the more efficient way of transport. Here he shows us how humans walk. I've spent a lot of time finding and watching all of his online appearances and interviews and whatnot, and there have been multiple occasions where I just couldn't stop myself from bursting out laughing, because the way he explains things is sometimes it's just totally bizarre. So it took me a while to figure out why the car walks. So here's a less crazy explanation. The car walks because cars move in a linear manner. Think about it. The car moves linearly. And in a combustion car, for example, we use the linear motion of the piston, which we then convert to the rotational motion of the crankshaft and the transmission and the differential and the driveshafts and all of these parts, and then ultimately the wheels. And then we again convert back the rotational motion of the wheels to the original linear motion, because now the car has to move linearly. Electrical vehicles are more simple in the sense that they have less moving parts, but ultimately they are guilty of the same motion conversion sin. An electrical car has giant heavy batteries which it uses to power its electrical motor, which then spins a single-speed transmission and maybe a differential and whatnot, and then finally the wheels, and then again we convert the rotational motion of the wheels to the linear motion of the electrical vehicle. And physics teaches us that converting one type of motion to another type of motion multiple times doesn't just increase the number of moving parts dramatically, It also reduces efficiency. It's an efficiency loss. This is why none of the animals, they don't have wheels, right? Because animals too, they move in a linear fashion, but they don't have wheels. They didn't evolve wheels because they didn't want to convert one thing to another. Well, none of them have wheels except that one weird spider from Animal Planet that sort of moves like a wheel. Apparently some bacteria have wheels. Anyway, none of the cool animals have wheels, and we name our cars after cool animals, so it makes sense, right? Explanation approved. Now, the Rosmar car doesn't just forego the conversion of one type of motion into another. It converts nothing into nothing, and it also doesn't have an engine, no combustion engine of any kind. It doesn't have any kind of transmission or differential or electrical motor, and it doesn't even have any kind of big batteries. It just has a conventional 12-volt lead-acid battery, yet without any of those parts, it is somehow capable of absolutely incredible achievements. By the way, I think that the top speed claim is absolute nonsense, but acceleration is definitely possible. We're going to crunch some numbers later in the video. For now, let's explain how it works. At the very heart of the Rosmar car, we have this, which is a double-acting air cylinder. Inside it, this black part is the piston, which is sealed against the cylinder wall. Now, if I release air here into this port, into this side of the cylinder, and I vent this side into atmosphere, the piston will move in this direction. Now, if I switch and I feed air to this side and vent this side to atmosphere, the piston will move in the opposite direction. And that's really all there is to it. We attach a wheel to the end of the cylinder, we move the cylinder back and forth, and that makes the car move. If we attach a wheel to the end of the cylinder and move the cylinder back and forth, doesn't that just make the wheel roll back and forth without the body, the rest of the car, going anywhere? And this manual connecting and disconnecting of the air supply, there's no way that the actual car works like that, right? Right, I agree. This is not very representative of the actual car, so allow me to fix that now. Allow me to install some wheels and some electrical valve control. Here it is, ladies and gentlemen, the ugliest thing that anyone has ever posted on YouTube. The absolute pinnacle of DIY offensiveness. But it works, I think. Now, the first thing we need to do is to fill up our fuel tank. And now, the moment of truth. Okay, let's try the other way. Okay, that works. Let's see if the other wheel has more traction. Nope. So this is the problem we have. The tire is slipping against the wheel. So my trick here is that I 3D printed a one-way bearing and then designed it to fit inside a Lego tire. This rolls in one direction normally, but if you try to rotate it or roll it in the other direction, you try to force these little rollers into an ever smaller space, which is of course physically impossible, and that makes the tire roll in one direction normally, but break in the other. So we want it to break when we're pushing the cylinder out, and if it breaks strong enough, if it has enough grip with the surface, then what's going to happen, instead of the tire going back, the rest of the vehicle, which has wheels and can roll freely, the rest of the vehicle will move forward. Unfortunately, in my case, that didn't work because, as I said, the tire slipped against the wheel. So now I'm going to lock it to see if that helps it work. Of course, now it can't roll in any direction, but doesn't matter. It's just a test. It spun the tire even with a zip tie. Okay, I'm gonna try cheating and using the wall. Haha. Okay, it kind of got twisted a bit, but it moved. It moved. And back. Okay, it covered half a table's length. So we have some stability and traction issues. We have stability issues because, as you can see, my wheels are free to flop around, rotate like this. On the real car, they are on rails, so this never happens. And we have traction issues because my one-way bearing 3D printed thing didn't really work with the Lego tire. And the fact that we don't have any weight pressing down here on this side on the wheel and the tire doesn't help either. Now, the real car, of course, doesn't use a one-way bearing. If it did, it wouldn't be able to go in reverse. Instead, on the real car, we simply use the brakes. When the cylinder is extending, the disc of the wheel attached to that cylinder gets clamped. This means that the tire stays put, and because the friction force of an actual car tire with the weight of an actual car chassis above it is massive, the tire definitely doesn't go anywhere, and instead the rest of the car, which is free to roll, moves forward. When the cylinder retracts, the disc brake is released, and so the tire and the wheel are free to roll forward back to their starting position. Now, this part right here is called a solenoid. Essentially, it's an electrically controlled air valve responsible for the proper functioning of this vehicle. So we have air coming from our tank to our air inlet, and we have two possible outlets and two vents. Inside the solenoid, we have a plunger which moves and covers and uncovers air passages between the inlet and the outlets. In its normal, unpowered state, the solenoid sends air from the inlet to one outlet and allows any pressure present in the other outlet to escape through the vent. When we apply electricity, in this case 12 volts, air from the inlet is sent to the other outlet, while any air remaining in the first outlet is vented. This allows us to send air to the two different sides of an air cylinder with the flick of a switch. As you can see, the solenoids are controlled by this electronic module right here, which is part of something called Cyberbrick. Cyberbrick is an ecosystem of modules, joysticks, switches, and motors that allows you to build pretty much any kind of radio-controlled vehicle you can imagine. If you don't want to design, configure, or program anything yourself, you simply buy the Cyberbrick kit, download one of the approved models, print, assemble, and have fun. When you get tired of your toy, you pick out a new one from the thousands of different models available on MakerWorld, you print it out, and then you reuse the same Cyberbrick components to power and control it. Essentially, you can build and explore an almost endless number of different RC models with the same Cyberbrick kit. Your only cost is a few bucks of filament. If you want to make something totally different and custom and ugly like I did right here, then you draw it up, print it out, and you hook up your Cyberbrick module to your PC to configure it to do whatever you want. You can even specify events that get triggered by other events, and if that's not enough, there's support for MicroPython, so you can code your vehicle to do super complex stuff. Basically, if you're into engineering or robotics or mechanics or anything similar, then it's pretty much impossible to get bored of Cyberbrick, and it makes a great learning experience for kids. If you want to check it out yourself, links are below. Now, what's interesting is that Cyberbrick was not designed to power solenoids, but as you can see, it works just fine. It works because the electronic module supports 12 volts. And I just configured one of the DC motor outputs to provide 100% of the power when I flick this switch. And all this wants is 12 volts DC, just like a DC motor, so it works perfectly fine. And it also means that you can power all sorts of different things using Cyberbrick. Something you might have noticed is that a lot of the weight of this very heavy model rests on these very thin little piston legs. And being 3D printed, you might expect them to break, but they don't. They don't because they're made from the most impressive PLA filament I have ever seen. Yes, this is PLA, but it's something called PLA Tough Plus. Watch this. Haters might say that the video is reversed, so I'll do it with my face in the frame while talking. So basically, this is a super strong, non-brittle PLA filament. You can bend it, as you can see. It goes a bit white. You can bend it, and you can bend it back. And it's still going to retain a lot of its strength. You can actually bend it multiple times in multiple directions and it will not break. It prints just like normal PLA, super easy, zero tweaking, but it most definitely does not break like normal PLA. Now it's time to address the elephant in the room. As you have probably figured out by now, this is a compressed air vehicle. This big lemony part here is the air tank. By the way, a 3D printed pressure vessel. It did 60 psi or 4 bar many times without issues. Maybe it can even do more, but I'm afraid to try. Anyway, it's just like the real Rosmar car, which is a compressed air car. This is why it doesn't need engines or e-motors or batteries, because all it needs is compressed air to run. Zero emissions. But there's a problem with compressed air cars, and that's that they have been tried before. Big names, Tata from India, Peugeot from France, many other names, millions upon millions of dollars of investment into many of the projects, yet they all failed. None of them ever reached actual mass production. But the Rosmar is different. It's different because it does one important thing differently from all the other previous failed compressed air cars. The mistake all previous compressed air cars made is using engines. Some had multi-stage pistons, others tried funky vane engines, but they all used some form of engine. When you release compressed air into an engine, it acts just like combustion. It expands. As it expands, it drives the piston down. But air expansion creates a problem, and you may have experienced that problem if you ever emptied an air compressor and noticed ice forming at the air outlet. When we compress air, we do work on the air. We increase the number of air molecules in the same space, which causes more of them to bump against each other more often. This work done on the air increases the potential energy in the system, which we measure as heat. But after some time in the tank, the air eventually cools down to ambient temperature while still having pretty much the same potential energy stored in it. When we release the compressed air to move the piston, the air expands and uses up its potential energy, which means the temperature must drop. And it does. It drops very rapidly. This is something called expansion cooling. We use this property of gases in refrigerators, air conditioning, and other devices. But in an engine, expansion cooling is a problem. When air cools down, it becomes more dense. It shrinks, and that means that the pressure drops. Expansion decreases. We don't want less pressure, we want more pressure because we use pressure off the expanding air to drive the piston down. If there's less of it, we extract less work from the energy stored in our tank, which means less power and less range. This is one of the reasons why all previous compressed air cars had pathetic driving range. But this is where the Rosmar concept really shines. All the other compressed air cars had engines. And that means the maintenance, friction, and moving parts of an engine, but it also means that every piston stroke is very, very, very short. The average engine needs between 50 and 100 piston strokes just to cover one car's length. The Rosmar can cover it with just one stroke. Because the piston stroke is much longer, takes much more time to complete, it gives the expanding air the opportunity to absorb much more heat from its environment, which offsets most of the negative effects of expansion cooling. Okay, that's great. But there's another problem with compressed air, one that's not so easy to solve. A 50-liter tank of gasoline contains around 1,700 megajoules or 470 kilowatt-hours of energy. A lithium-ion battery that occupies the same space as a 50-liter gasoline tank can store around 65 megajoules or 18 kilowatt-hours of energy. Now, a 50-liter compressed air tank at 350 bar stores the amazing amount of 18 megajoules or 5 kilowatt-hours. So even if your air cylinders are 95% efficient, this is simply not enough. This is the real problem of compressed air cars. Wait a second, there's a simple solution. Let's just double the pressure. 700 bar should double the energy. 1,400 bar should make it even better than AVs, right? Wrong. Doubling the pressure does not double the energy. A tank at 700 bar will not get us 10 kilowatt hours. It will get us something closer to 8. When you pressurize something that's already pressurized, you're essentially squeezing something that's already compressed, so each increment stores progressively less additional energy because there's a limit to how much you can compress air. Also, a tank that can hold 700 bar needs to be twice as strong, which makes it bigger and heavier and offsets the less than twice the energy gained from the pressure increase. Another problem is the very act of compressing the air in the first place. You experienced this if you ever used a manual air pump. The higher the pressure, the harder you have to push. It's a game of increasingly diminishing returns. Even if your air cylinder is 100% efficient, which is impossible, the act of compressing the air itself is pretty inefficient, around 40 to 50%. And you can feel where the rest of that efficiency went if you touch the pump after using it a lot. These poor energy storage properties of compressed air also explain why a top speed claim of 600 km per hour is a blatant lie. The current record holder for the fastest production car is the Yangwang U9 Extreme, which managed a top speed of 496.22 km per hour. Just to reach this speed, the Yangwang required around 10 kilowatt-hours of energy. Now, the Yangwang is very heavy because it's an EV, so let's assume our compressed air car is much lighter. Let's say 1,500 kilograms because it doesn't have an engine or transmission or differential. To only reach 600 km per hour, it would still need around 21 kilowatt-hours of energy, and that's because kinetic energy grows with the square of speed, while the energy needed to overcome aerodynamic drag grows with the cube of speed. 21 kilowatt-hours of energy would require an air tank of around 250 liters at 350 bar. That would be very big and very heavy, but not impossible. But here's the actual nail in the coffin. A battery at 90% and 20% charge still delivers the same motor performance. Gasoline delivers the same performance down to the last drop. A compressed air tank does not. As the tank empties, pressure inside falls, and so does the maximum possible performance, which means that the car would have the least power available right at the highest speeds where it needs to overcome the highest air resistance, and thus reaching 600 km per hour with the Rosmar H or any other compressed air car anatomy is the realm of science fiction. But can it do 0 to 100 km per hour in 0.3 seconds? You bet it can. Why? Because 0.3 seconds, that's the time it takes the pneumatic cylinder to extend. If you shove enough air into an air cylinder, you can get it to extend extremely quickly. And it can even reach 100 km per hour momentarily during that extension. And remember, the front of the car moves at the same speed as the extension of the cylinder. So you, as a passenger in the front of the car, get propelled to 100 km per hour almost instantly. Of course, whether the vehicle can maintain that kind of crazy acceleration as the tank empties, well, that's an entirely different question. Wait a second, hold up. 0 to 100 in 0.3 seconds, that's 9.4 G. That's the kind of acceleration that causes neck injuries and people to pass out. Top few dragsters, they need special giant rear slick tires to achieve only 5G. So how in heaven's name does Rosmar plan to do it with what looks like a normal street car tire? Well, they don't plan to do it with the tires. They plan to do it with wheel chocks. You can actually see them both on the concept and on the prototype right behind the wheel. These chocks get lowered to the ground and then they vacuum themselves to the surface to create extreme amounts of grip. If you have compressed air, all you need to create vacuum is an ejector, and the Rosmar has plenty of them. Basically, you shove air through a venturi, and just like in a carburetor, the venturi creates a low pressure zone, i.e. vacuum. The more air you send faster through the venturi, the higher the vacuum you can create. So it can launch itself at neck-breaking speeds. But here's something that it can't do. Comfort. Do you notice a glaring problem with the Rosmar? No suspension. Imagine launching yourself at 9.4 G into a speed bump with no shocks or springs. You cannot implement a traditional suspension between each wheel and the body of the car because the distance between the wheel hub and any fixed point on the car body is constantly changing. A suspension strut needs at least 2 fixed points to function. So the only thing we can do with the Rosmar is to suspend the entire body on the frame, which would consist of the frame itself and the air cylinders, wheels, hubs, brakes, rails, and probably even the tanks. This leads to a lot of unsprung mass and very questionable handling. The other problem we have with comfort is that propulsion comes from extending cylinders. So passengers inside constantly get jolted back and forth as the cylinders fire. Well, yes and no. Comfort does proportionally increase with the number of pneumatic cylinders. When there's more of them, there's less time between each one extending, so they can sort of overlap to make the ride a bit smoother. So the 4-cylinder concept is likely okay-ish when managed properly, whereas the 2-cylinder prototype is probably not smooth at all. The other problem that it has is that when one cylinder is extending while the other one is retracting, it creates a rocking couple which is trying to basically turn and twist the vehicle, which may very negatively impact turning. So it's not looking good for the Rosmar, but wait, we're not done yet, because there's one thing at which this car can outshine any conventional wheeled vehicle ever made. Conventional vehicles struggle in low traction conditions and with severe inclines because their wheels start slipping and so they go nowhere. But the Rosmar H can simply suck itself to the ground using its vacuumatic wheel chocks and then move the body to overcome literally any terrain. And this is exactly what the original patent is all about. This is what Mr. Roșca actually designed, a technology that is ideal for exploration, mining, rescue, military, you name it. It's a vehicle capable of covering the most extreme terrain. Okay, so then why advertise it to the general public as an asphalt-based automotive revolution? Because that's how startups work nowadays. You make the craziest, most bombastic claims possible to attract the most media attention possible, which then attracts the largest first wave of investors possible. You use this initial financial backing to hopefully develop the technology enough to make it attractive to a large military contractor, and then you just sell all of it. This is pretty much the path taken by a liquid piston and a Katie's power, for example, albeit with less crazy claims than Rosmar. In the end, no revolution takes place, but a large sum of money does exchange hands if the technology becomes mature enough for a given application. So, no, you won't get to drive around in a compressed air pogo stick, but the technology is definitely very interesting, and I hope that it was a good learning experience. I know it was for me. As always, thanks a lot for watching, and I'll be seeing you soon with more fun and useful stuff on the D4A channel.